So I'm going to talk on this title that I gave, Coarse-graining, Renormalization, and Quantitative Homogenization. So I'm going to try to explain what all that means. Let's see if I can go. Yep. So like Paul said, I'm mainly interested in homogenization the last 10 years or so. And the main model equation is this parabolic equation, or just maybe the simpler elliptic one. And you should think of this matrix A as being, can you see the red cursor as well? Okay, so I can point. So you should think of this matrix A as having a lot of microscopic wiggles, which are specified in some way. Homogenization refers to the solutions limiting on macroscopic scales to a simpler equation. Usually that takes the form of, at least in this elliptic case or parabolic case, an equation of the same form, but the matrix A is now deterministic and constant. So we typically write A bar. And these are called the effective or homogenized coefficients. Okay. So to put a finer point on that, I'm interested in quantitative homogenization, which means I essentially want to find a rate of convergence in this macroscopic limit. And I want to explain first why this is an interesting project by bringing two examples kind of out of left field. And then I'll circle back and explain, sort of give an overview of the theory and try to explain some of the key ideas, kind of from a bird's eye view. And then in the last few slides, I'll present some of what I think are the open problems. Okay, so when I give talks, I usually have either a probabilistic audience or an audience of analysts. And so for the probabilists, I don't have to motivate the problems, but I have to motivate the need to do the analysis. And here I have a bit the reverse. So I'm going to bring up a problem that comes out of statistical physics. Okay, so this is called a gradient interface model. So the basic setup is you have a discrete surface evolving in time, 5t. So you think of it as a graph of some function 5t, which is a function from zd to r. And so you think of every little node in zd as having a little particle over it. And what happens is each of those particles undergoes Brownian motion, which moves it up and down. But the particles are also connected by little springs to the nearby particles, their nearest neighbors. And those springs exert an elastic force. So you can't, it's not just infinitely many independent Brownian motions. That would be boring. There's some coupling, of course. And the coupling is given by this potential V. Okay. And so we model this this surface that's evolving according to this stochastic differential equation. You have, it's actually a system of countably many stochastic differential equations, I guess. At every point x, it evolves like this. You sum the v prime of the difference. This is like the little discrete gradient at the site x inside v prime, and that's the drift term that kind of pulls, the spring is pulling it back. And then over here is a Brownian motion, and you have an independent one for every point x. Okay, so that's the setup. Probabilists will often not specify the dynamics and instead say that they're interested in the stationary measure associated to this, which is given by some Gibbs measure, which I won't write down. Okay. Anyway, there are a lot of interesting models that are of this form. Okay. So I put the dynamics up here. Now, in the case that V is C11 and uniformly convex, then this is kind of a toy model that was introduced a while ago in statistical mechanics, probably in the 90s or even the 80s. I don't know. Paul, our chair, would know better than me. And it's studied by a lot of well-known math physicists. And let me give you a sample theorem. So this goes under the name gradient interface model, sometimes grad phi model, sometimes Ginsburg-Landau model. I don't know how Ginsburg-Landau gets in there, but anyway, here's an interesting result that tells you kind of what's going on for this system. This was proved by Jacob and Ola Spohn in 2001. Again, I'm talking about the dynamics, the sort of the version of this for sort of stationary things where you just look at the invariant measure and you freeze it at some time and just look at the like a time slice. Was studied previously by Spencer and Nadoff and Spencer. So the first thing that you want to know is that if you start this surface from a smooth initial condition that's kind of spread out on some macroscopic scale, much bigger than the size of the lattice. Then you'd like to know that if you evolve this system, that it has a hydrodynamic limit that is kind of, as that scale separation goes to infinity, you get a limit that's deterministic. And in this model, you can prove it. These dynamics, these discrete dynamics, converge as the lattice spacing goes to 0, really, to this parabolic PDE, where there's some sigma, which is another uniformly convex C11 function, which is kind of an effective coefficient. It's the effective Lagrangian, if you want, of this nonlinear problem. And it solves this divergence form equation. Okay, so that's that. At leading order, what happens? The probabilists, of course, are interested in the fluctuations around that. And so they'd like to show that if you subtract the solution of this equation and look at the error, like what's left, the signal, that they can understand that kind of noise as in some kind of as some kind of limit of some stochastic process or random field. And in this case, the random fluctuations behave like a Gaussian free field with covariance matrix A. So there's some, or A bar. There's some A bar so that you get a Gaussian free field. So a Gaussian free field is like a high dimensional Brownian motion. Okay, and in this case, it should really be a time-dependent version of the Gaussian free field. So it's really the time slices that are limiting to the Gaussian free field. Okay, so that's the theorem, and this sigma is called the surface tension. So they refer to it as the surface tension of the model. It's kind of the effect of those springs, if you want. And so some questions you may ask are: is sigma C2? Which is kind of important if you look at the parabolic equation. You won't have classical solutions unless sigma is C2, probably C2 alpha. And if sigma is not C2, then your numerical method, then you won't get a good rate of convergence in the hydrodynamic limit, and you won't, the solutions are not going to be so regular. And they expect that this A bar is actually the Hessian of sigma, I guess, at the point 0, at 0. And if that were true, that would be a relationship between the this sort of hydrodynamic limit and this fluctuation limit, and they call that a fluctuation dissipation relation. So it's kind of like the reason that you expect that is that if you linearize this equation, then you should get the sort of equation that describes the fluctuations, which would be like a Laplacian with A bar, like a divergence A bar grad U. Okay, so they expect a kind of commutativity, the physicists do, between this limiting procedure and the linearization. Okay, and so anyway, I want to sell the homogenization methods by saying that this problem was open for a long time, for 25 years, and it wasn't just a problem that was never mentioned. It was mentioned all the time, and unfortunately, we're still stuck. This problem's still open. Despite a lot of effort, it remains conjectural despite serious effort. Funaki writes in 2003. Okay, so what were they stuck on? Why can't they prove it? Well, so we proved this actually with Paul Dario and Wei Wu, different versions of the theorem. Yes, sigma C2, and yes, you have the fluctuation dissipation relation. And the reason is that those dynamics, that noisy system that was evolving, was really, you could think of it as a discrete version of a PDE with white noise on the right hand side. So really, if you look at that, I mean, if that discrete thing were a PDE, I know it's not, because it's got the small scales are discrete, and that's not in the continuum. But if it were, it's formally of this form. It's a parabolic equation, nonlinear, with a white noise on the right-hand side. And then if you were to linearize this, its linearization would be a parabolic equation in divergence form, linear, but the coefficients here would be whatever this matrix with the solution of the dynamics plugged into it, which is going to be noisy because of the white noise. So this phi is random and noisy, and you're plugging that into this. I didn't write the V. I should have written the V, D2PV. This thing is going to be like a random coefficient field, okay? And it turns out that homogenizing this equation is giving you the hydrodynamic limit. Okay, that's not news. But homogenizing this equation gives you the fluctuation dissipation relation. And if you can homogenize them both in a quantitative way with uniform rates of convergence and stuff, then you can start to make limits commute. And so you can start, a linearization is a limit because it's taking a derivative basically. So you could make this diagram commute, and the making of that diagram commute is the proof. Okay. And so in order to commute limits, you need quantitative rates. So in hindsight, it's kind of obvious that, and the reason they were stuck is because they were using qualitative homogenization instead of quantitative homogenization. So we unstuck them just by getting a rate. Okay. This is, so like I said, this is kind of a toy model when the V is uniformly convex. The mathematical physicists are much more interested in other models in which the V, it has a similar form as that model that I wrote, but there's more, the V is nastier. It's not uniformly convex. It may not even be convex, or if it is convex, it really is having flat parts in its graph. Like the solid on solid models, like the V is the absolute value of X, so that all of the diffusion happens at the origin somehow. And there's other models, and it's plausible that homogenization methods could attack these models. So that's, anyway, so this is one motivation. And in order to attack these other models, we need a homogenization theory that works for degenerate equations, things that are very, very degenerate. Okay, so keep that in mind. Okay, next, sort of out of left field application. So this is a project that I've been working on with Vlad Vikol since the pandemic started, and we're not done, but we're still trying to write the paper. It's about turbulence in fluids. So I wrote down the Navi Stokes equation for you. Sorry, my screen's doing something really weird. Okay. I wrote down the Navi Stokes equation for us here, just so that I could remember it. There's a Laplacian, and there's a drift term, and the drift term is the solution is pushing itself. It's like advecting itself, right? That's how Navier-Stokes works. Okay, so there's a whole talk I could make about this. I don't have time, but just to say that Komogorov's zero law of turbulence says that if you have a turbulent fluid, you should see energy dissipation of order 1, even if nu is very, very small. So like the limit as nu goes to 0, the dissipation of kinetic energy should still be of order 1. Okay, so the Laplacian still does something, even if you let send nu to 0 in a turbulent fluid. This is called anomalous dissipation of kinetic energy. I saw there's somebody, Teo's in the audience. He knows more about this than me. But the idea is that there's an advection term, okay, in the equation. And until if you look at length scales that are large, the advection term wins, and the Laplacian does nothing. So what the advection term should do in a turbulent fluid is move energy to smaller and smaller and smaller and smaller scales until finally the Laplacian can see it and kill it. And that's how this should work. There should be a cascade, okay? And an embarrassing question for the field is that, does anyone know an example of any vector field, which is a solution of this advection diffusion equation, which has an anomalous diffusivity, okay? Now, Theo knows how to do that, I think. Because in some sense, I learned about this problem from a nice talk he gave at Courant about it. But I want my B to be as kind of close to a real fluid as possible. Okay, so I want anyway. So I don't want to handle the full Navier-Stokes equation because it's too complicated. So I look at this advection diffusion equation because it's simpler. The B and the U are not necessarily coupled, and I just want to see if I can make anomalous diffusion. Like, what would the vector field look like? So what Vlad and I do, if we can finish writing the paper, is that we make a vector field which is almost C1/3, okay? And it has a kind of infinite number of scales built in a fractal way, okay? Now the base fractal is a shear flow, and we alternate them in different directions so that all the directions get a turn. And we alternate those in time, but then the size of the shear flow gets smaller and smaller and smaller and smaller as we put more and more and more scales into the problem, and we put infinitely many scales in until so that the vector field is C1/3 in some C1/3 way. Okay, so I'll be vague on how this construction happens, but we do it. And then once we have our vector field, then we look at the advection diffusion equation. We go to the first scale at which there's something non-trivial happening, because scales that are too small, the Laplacian kills it. So depending on the parameter in front of the Laplacian, that kappa that I had, we go to the right scale for balancing the advection and the Laplacian, and then we start homogenizing up, okay? And we go up, 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 one scale at a time, and every scale gets homogenized one at a time. And what happens when you homogenize with a divergence-free vector field advecting you is that the effective diffusion goes up. The mixing of the vector field increases diffusivity, and the homogenization can see that, okay? And so as you homogenize, the A bar matrix, if you want, gets bigger and bigger and bigger and bigger until finally you get to scale 1 and it's O of 1, okay? And you just need that the O of 1 that it is bigger than the error that you made going across that infinitely many scales. And if it is, then you win, you have anomalous diffusivity, okay? Because that homogenized matrix really does tell you the rate of diffusion or of dissipation, okay? So that's what we do. Now, this is my attempt at a joke. So is this a new idea to use homogenization in turbulent flows like this? Some of you may be thinking, didn't I read Papanikolaou papers, Papanikolaou, Fang Zhang, Andy Maida in the 1990s? But well, actually, apparently this goes back to the 1850s. So Busenesque, so I found out reading this book by Frisch, which is a wonderful book for me, knowing nothing about turbulence. So I thought, this is a really smart idea we have, like you do an inverse cascade of homogenizations. But it turns out that it goes back to the 19th century, and actually Busenesque and I think Saint-Véran or something in 1851 have kind of hand-wavy explanations of it. However, if it goes back to 1850, then why has nobody done it? Okay. Well, in Andy Maida's 350-page survey about this topic, he has an explanation. He says, basically, you can't do it because you don't have good scale separation. In homogenization, we need infinite scale separation. We don't have infinite scale separation because if you make a vector field and you start putting scales, when you put the second scale, you've already made a scale separation that's not now going to go to infinity because it's fixed there. And you're not going to get it to work. And anyway, there's infinitely many scales. And Frisch makes roughly the same point. He says, these ideas can maybe give some intuition, but they're never going to be formal. What you need to do it, Frisch says, is more informal renormalization group arguments, he says on the next page. Renormalization group arguments, not because those are, and those are not really, those are kind of heuristic, but at least you have a chance to kind of have some explanation. Okay, so we managed to do it. So how do we do it? Well, we put in the scales in a supergeometric way. So the first scale, okay, there's some gap, and the next scale has a bigger gap, and the next scale has a bigger gap. And the gap between any two scales is some very small power of the scale. Okay, so it's like epsilon m plus 1 equals epsilon m to the 1 plus a little number, and so that it goes down in a super exponential way. We compensate the gaps because when we have a gap, we're not using enough the space and the amount of scales that we have to work with. We're skipping a bunch of scales, which is not smart if you want to make the thing enhance. So we have to then make the vector fields a little stronger, those shear flows, to compensate the fact that we have those gaps. But now we have a problem because when we make the vector field stronger, that corresponds to, in the homogenization problem, a problem with large contrast. So it's like we have a matrix with large ellipticity contrast. And while we have big gaps, they're not that big compared to the contrast. And so we have to make sure, we have to work out that there's room to homogenize. And so we really need a quantitative homogenization theory that says, by this scale, you've homogenized even when you have large contrast. Okay. And in order to do that, we use the fact that we can make our wiggles periodic. If they would be random, we would be dead. And in the periodic case, we have infinite order homogenization, and we can be very, we can squeeze every drop out of the periodic homogenization theory to get a theory that has optimal dependence and ellipticity. And that's what we do, and it works, if we can, I think. Anyway, part 2. So now I'm gonna, so that was the motivation. I gave you 2 problems where homogenization kind of maybe unexpectedly arises from math physics. those are the things that kind of motivate me personally. I like those problems and I want to use analysis to solve them. And now maybe if you're an analyst and you don't care about those problems, then this is the part of the talk that you may get something out of. I'm going to talk about what is the quantitative homogenization theory and how does it work and what are the kind of key ideas. When I do this, I'm going to keep a very bird's eye point of view. I'm not going to go into the details too much. Okay, I'm going to try to give you intuition, a couple theorem statements and ideas of how things fit together, but not I can't do the proofs. Okay, so what is the basic problem set up for me? As usual, I have a coefficient field A of x. Let's say that it's uniformly elliptic, which means it's bounded between two multiples of the identity. Let's go ahead and even assume it's a symmetric matrix. Okay, so I don't have problems. I don't have extra things to worry about. And let's assume that A is as nice as possible from a statistical point of view, that it's drawn, it has a finite range of dependence. Okay, so A is going to be a random object. It's going to be a random field, but I want its randomness, I want its decorrelations to be as nice as can be. So I'm going to assume that if you have two sets and you look at A in those two sets, and those sets are separated by a distance of 1, then the behavior of A is independent in each of those sets. Okay, you encode this with sigma algebras, but we let the lawyers write that part of the paper. We also assume that A is statistically stationary, so that when we compose with the translation by ZD, by elements of ZD, that it doesn't change. This allows an example of such a problem is if A were a checkerboard. Like imagine that you have a checkerboard, an infinite checkerboard, and in every square you flip a coin between 1 Laplacian and 2 Laplacian. Okay, and your A is either 1 times the identity or 2 times the identity, and then you want to solve the elliptic equation corresponding to that. Okay, so that would be a perfectly admissible, and that's really if you have that example in your head, then that's what's going on. Okay, so most of you, or many of you at least, know about elliptic homogenization, but let me just go over the basics so I can kind of introduce my language. So the way I think about it is that we take as an ansatz so here I'm going to introduce that parameter epsilon that I don't usually introduce and put dot over epsilon in the matrix A instead of looking at a large domain with epsilon equal to 1. And that's because it makes the kind of heuristic derivation easier because it helps you keep track of scalings. So we're looking at this elliptic equation with A of x over epsilon as the coefficient field. So the lattice is small. And we want to kind of do an expansion in epsilon, an asymptotic expansion. What should it look like? Well, a good guess is that it looks like some macroscopic function in green here, u of x. Macroscopic meaning it's kind of smooth on scale 1. Okay. And then all of the microscopic wiggles are encoded in some function here, phi, which we call the corrector. And phi should only care about the kind of local slope of the macroscopic function, which is the gradient of u at the point x. Okay, so it should only care about that because the equation's translation invariant. Like I add a constant to the solution, and it's a solution. Okay, and if you imagine that, okay, so this matrix A is changing really fast on scale epsilon. The gradient probably has to change really fast on scale epsilon to compensate for that in order to keep it a solution. And so if we put an epsilon in front of the phi, then we take its gradient will be of order 1. That should probably work. Okay, and so you look for an ansatz of this form. You plug into the equation and you compute, and you try to see if you can design the u and the phi in order that the right-hand side is small by means of epsilon. Okay, so when you do that, you find that you can do that as long as u solves the homogenized equation with A bar. Now, A bar is determined by the average of the correctors, and the correctors solve this equation. So these 3 things go together, and if they're all satisfied, then when you plug in this guess into the equation, the right-hand side is going to be small in the h-1 norm, and that means that you've made a guess for the solution. And therefore, if you have a real problem that you solve and you want to compare it to the real solution, you know that your guess is almost a solution, so that when you subtract them, the right-hand side is small, and then you can solve an auxiliary problem to kill that right-hand side, and that's your error. Okay, so that's how it works. And when you actually plug this in, you can write down an identity, which is a formula to see that this is happening. Okay, so the formula says that this divergence form operator applied to my guess equals, okay, I get an epsilon here. I get the divergence of something. So that's a good H-1 thing set up, right? I just have to estimate the L2 norm of what's inside. I get the second derivative of the macroscopic function. And I get this sum of things, A times the phi, and then I have the S, okay? And these things are evaluated at X over epsilon, even though I didn't write it. And this one's evaluated at X, okay? The S's are the flux correctors. They're the potential functions for the flux. This is a divergence-free field, and there's a potential for it, a matrix potential, and you call that S. And the L2 norm of the S, because the derivative of it is this flux, its L2 norm encodes the H-1 norm of the flux, and the L2 norm of phi encodes the H-1 norm of the gradients. So these guys' L2 norms here are quantifying the weak convergence of the fluxes and the gradients weakly, okay? And you see that, so that this, the weak convergence of the fluxes and the gradients on the right-hand side gives you the homogenization, okay? So that's how it works. All right, so this means that the corrector equations are important and we should try to understand them. And that we should try to understand exactly how big the L2 norm of the corrector is. And maybe we should just try to understand these weak limits, actually. Okay, so that's the project, is that we want a rate of convergence for these weak limits under these assumptions. Okay. Now, in the case of periodic homogenization, really periodic, where everything's completely periodic, you're done, because this is a periodic function. This is a periodic function. There are L2 periodic functions. You're making them oscillate on scale epsilon. The H-1 norm of that is epsilon. By the Poincare inequality, you're done. Okay, there's just nothing to say. If you take any periodic function in L2 and then you scale it by epsilon like that, then its H-1 norm is epsilon. Okay, so in the periodic case, you're done. In the stochastic case, the fun begins, because this is actually the whole problem, right? In the stochastic case, you can't just one-line this thing into having a rate, okay? And the reason is that somehow in periodic homogenization, quantitative information passes from the coefficient field to the solutions, or to the correctors anyway, in a very easy way. The coefficients are periodic, so the correctors are periodic, and periodicity is great quantitative information in this context. In the stochastic case, you can pass information from the coefficients in the most kind of weakest way. So if you know the coefficients have ergodicity, then the correctors will have ergodicity. And so you know that, and that's how you prove qualitative homogenization. However, it's difficult to pass quantitative information. And you can think of it like this. The coefficient field would be independent, like we described, a checkerboard. And you solve the corrector equation somehow, right? You're solving an elliptic equation. Are the correctors going to be independent of itself in different cubes? Obviously not, right? And it's not going to be independent of the coefficients, because it's going to see the coefficients everywhere. And if you change the coefficients in one cube in one spot, the correctors are changed everywhere in space. And you need to actually figure that out, that correlation structure. And so that's what's hard, is that we have to tame the correlations. Okay. So this is where the fun begins, as I said. Let's go ahead and do a back of the envelope calculation just to see what we expect to happen in the random case, because it's actually not the same as in the periodic case. Okay, so this is a fun back of the envelope calculation. And this back of the envelope calculation is actually what the proof is in the end, by the way. So it's not a dumb back of the envelope calculation, it's a smart one. So let's go ahead and assume that we're in the case where A is actually really close to A bar. What I'm going to try to do here is I'm going to try to kind of linearize the randomness around A bar. Okay, now linearizations work when you're close to the limit. So let's just go ahead and assume that the whole field brutally in L infinity is close to the limit. So this is just, you assume that you're in the small contrast regime. Okay, let's look at the corrector equation and let's rewrite it like this. So I'm going to put A bar on the left-hand side so that I have a Laplacian. Laplacians are nice because I can invert them very easily. I know how to invert with a Laplacian. Here, I can go ahead and smuggle in a minus a bar because after all that, the divergence of a bar E is a constant, so its divergence is 0. And so therefore the thing under the divergence sign is O of delta, okay? And then I have to put the term where I pay the price for having switched the A and the A bar on the left, and I compensated on the right. Again, this is of order delta. Okay, so everything on the right-hand side is of order delta. Stands to reason, let's not worry about the fact that we're in the whole space or whatever, just for a second. Stands to reason that the gradient of the corrector should then be of order delta if we just had normal H-1 to L2 estimate like that. And if the gradient of this is of order delta, I can go back to this term, see that now that term is of order delta squared. And now I'm going to wave my hands and say, delta squared is a quadratic error, let's ignore it. And just then throw it in the garbage and look at this and look at what's left. And what's left is basically Laplacian equals divergence of independent stuff, like independent checkerboard. It's just the checkerboard bouncing around and you're taking its divergence. Now, from the point of view of a very large scale, if you zoom out, this is just white noise. It's the divergence of white noise. So your equation should look like Laplacian is the divergence of white noise, okay? So that's what we expect the corrector to look like. It's Laplacian, or at least with a bar, equals the divergence of white noise. Now, this is an important object in probability. If you think about what it means, if you have Laplacian equals divergence of f, where f is some vector field, what you're actually doing is you're computing the Helmholtz-Hodge projection of that f. All right, so if I give you any vector field, and you want to say, okay, that vector field may not be a potential. If I can integrate in a loop and not get 0, but I want to find the closest potential in a kind of L2 projection sense to that f. Find the gradient field that's closest to f. Then you would solve, the normal equations in linear algebra, right? They say like if you want to solve the least squares problem, you solve a star A equals a star B. And so in this case, A is the function which is the potential. Sorry, A is the nobla symbol. A star is the divergence. And so you actually get Laplacian equals divergence of the vector field. Okay, this turns out to be the Gaussian free field. So what the Gaussian free field is, even though the probabilists don't usually like to or even know that this is true, is that you take vector white noise, you project it onto the space of potential fields, and that is the Gaussian free field. And that's why you think of it as a generalization of Brownian motion to higher dimensions. It's like, if white noise were a potential, what potential would it be? Okay, because it's a Gaussian field and it's so simple and natural, we understand everything about it. It's a Gaussian field and its correlations are given by the Green's function of Laplacian. And if you have a Gaussian field and you know its correlations, then you sort of understand everything about it. One thing to note is that we want to understand the spatial averages of the gradient of our correctors, right? So what is it for the Gaussian free field? All right, the spatial averages, if you understand the spatial averages, that's what quantifying the weak convergence to 0 means. So for the Gaussian free field, if you took a function with mass 1, kind of spread out on scale r, like a smooth function, and you just stretch it, but you keep its L1 norm equal to 1, and you multiply by the gradient of the GFF, and then you ask, how big is it? Well, it's going to be a function with fluctuations that oscillate like this. They're going to be of order r to the minus d over 2. So the typical size of this will be r to the minus d over 2. The same size you would have if this gradient here would just be an IID independent field. So like if you average, because the number of random variables you're averaging, or the number of cells you're averaging over, is r to the d. And so the CLT scaling would be the square root of that, right? So you would get, the size should be 1 over the square root of the number of random variables. That's why you get r to the minus d over 2. Okay. So this is what we want to prove for the corrector. So how are we going to tame these correlations? Okay, so this was a problem which not much progress was made until 2010 or so. What happened was, as I understand it, is that Spencer was studying the grad phi model, the same one that we were talking about earlier. Tom Spencer with the student Nadaf, and they wrote 2 papers, one on the grad phi model, which uses homogenization to prove something, and one on homogenization, which uses sort of intuition from the grad phi model to prove something about homogenization. And the homogenization paper was rejected and never published or something because the referee didn't understand. But it was a beautiful paper, and what their point was that you can use these sort of nonlinear, quote, nonlinear concentration inequalities to prove things in homogenization. So what you do is you say, well, assume I actually have a random checkerboard, okay? So I have a countable number of variables that describe my coefficient field, a countable number. So I have an infinite number of variables, and I can think about random variables on that, random variables of the coefficient field as just functions of a countable number of random variables. And if I have a Poincare inequality on that probability space that says that the variance of a random variable is controlled by the derivatives of the random variable with respect to those numbers, then I can use it. It's a Poincare inequality, and that's anyway how people in probability and statistical mechanics prove decorrelation, in fact. So you apply this inequality to these kinds of random variables, and you can prove homogenization estimates, okay? So they realized this, they had an unpublished preprint. They didn't make that much progress on it because they couldn't get the estimate, sort of the estimates that come from regularity in order to close and really prove a full theorem. And so then Antoine Gloria and Felix Otto came and really made a program out of this and made huge advancement. And for these checkerboard models, they proved this scaling in homogenization. And when I was a sort of a postdoc, this got my attention, and that's what made me want to work in the field. So they made big progress using these nonlinear concentration inequalities, and now it's a giant industry. It's like 2% of German GDP, I think now. Method number 2 is the method that we developed later. So we started working first with Charlie Smart, and then with Tuomo Kusi and Jean-Christophe Marat on a different idea, but sort of motivated by the desire to prove results like this, okay? So our ideas are about coarse-graining. So now I come to the title of my talk. What do I mean by coarse-graining? Well, what you do is you coarse-grain the coefficient field. If you have a way of it's the ultimate coarse-graining would be you replace the coefficient field by a bar. But suppose that you want to kind of make an unfinished homogenization at some finite scale. And you say, well, this hasn't had time to converge to a bar, so maybe it's kind of making it a slight error. But you, in any case, replace in every cube the complex coefficient field A of x with something that's constant in that cube and represents, this is what a bar would be in that cube. If it, like if you had to choose one matrix for that cube, what would you choose? Okay, so this is this is what I think of when I think of coarse-graining. And you think of the mapping, which takes R to the Courson coefficients at scale R. You think of that as a flow of scales from 0 to infinity, where the eventual limit is a bar. And we want to show that for R very large, you eventually get close to a bar, close enough that you can actually somehow make that naive small contrast computation actually just work. And then you can prove your GFF like that, okay? So that is the idea. This idea, I thought we had developed it, we had written a book, and then like a year ago, Guido De Filippis, my new colleague at Courant, he was reading through the old papers of De Giorgi and sent something to me. I guess Italians have the papers of De Giorgi by their bedside table, and they read it at night. But this idea goes back to the very first paper that was ever written on homogenization by De Giorgi and Spagnolo in 1973. So there's this funny conjecture in that paper, which basically anticipates exactly what we do. Their conjecture is false. It doesn't work like that. But these things that they're writing here, it's hard to see because I'm just flashing a slide in your face, but these things are half of our coarse-grained coefficients, okay? What are they writing here? They're writing the energy of the Dirichlet problem in a fixed domain. So one way to coarse grain the coefficient field in a domain is you pick affine boundary data, you look at the solution of the Dirichlet problem, you look at the energy of that thing, you normalize that by volume, and you look at that as a function of the slope of the boundary condition, and you get a quadratic form. So there's a matrix for that quadratic form, and you call that matrix the Corson coefficient field, and that's what DeGiorgi does with this thing. And what he writes here, what he's saying here is that this sort of is consistent with coarse graining, that if you have two coefficient fields, okay, and you want to estimate the difference on a large scale between the coarse grain coefficients, okay, it's going to depend, it's not going to be a true renormalization group map, because it's not just going to depend on the previous scale. It's actually going to depend on all the scales below that, but you get to discount the small scales with the geometric factor. So you really primarily depend on the large scales. And he says, you know, if you could prove something like that, this would be a really useful for quantitative estimates, he says in 1973. Okay, so I thought that's pretty good. Like, I don't even think the word homogenization was, he even knew to use the word homogenization to this problem yet. Anyway, so what are we going to do? Here's a high level overview of what our approach is. I still have 10 minutes, right? 8 or 10 minutes? I don't know. Okay, I'll go on. So there's 3 steps, okay? Now that I'm writing on one slide a summary of the proof that's in this book, the first 6 chapters. So the book is thick, and it's a couple hundred pages to get through this. But if you had to write it on one slide, here's what you would say. Here's the basic idea. We're thinking about this coarse graining, you know, as being like a flow. We start at 0 with the coefficient field A of x. We coarse grain as R gets bigger, we eventually get A bar at infinity, okay? And we want to show convergence to A bar almost like we want a rate of convergence like you'd prove. You know, a rate of convergence if you have like a nonlinear PDE and you want to show the solution goes to equilibrium or something. There's 2 steps. The first step is if you were close to the limit, can you linearize? Okay, but before you do that, you have to get yourself close to the limit with some nonlinear argument. Okay, and that's what we do. Step 1 is implement the DeGiorgi-Spagnola idea in some sense. Define good coarse-grained coefficient fields, show that they have good enough control on solutions and that they are faithful to the coarse-graining idea enough that you can make some iteration work up the scales. Like you iterate up the scales, kind of like the DeGiorgi Holder estimate iterates down the scales, and you get some exponent of convergence. Okay. Now that exponent of convergence is that's not what matters. What matters is that you've entered the kind of small contrast regime now in your coarse graining. Step 2 is to notice that step 1 puts you in the small contrast regime, which means you're close to being homogenized. And if you're close to being homogenized, that means you're close to a Laplacian in some sense. And that means you can borrow the regularity of the Laplacian, because the Laplacian has better regularity than just a generic coefficient field by a lot. And so this gives us what we call large scale regularity. Okay, so this was steps 1 and 2 were sort of what we developed with Charlie. And then step 3, which was at the time the hard part, was the thing we developed with Tuomo and Jean-Christophe, where we sort of, quote, linearize the noise and iterate to infinity, okay? And the basic idea is this, if you want to think about the renormalization map. In homogenization, people that know homogenization know that the homogenized matrix is between the mean and the harmonic mean, okay? And we think of the mean and the harmonic mean as being far apart. But if you're in the small contrast regime, the mean and the harmonic mean agree at leading order. They're both the mean, and they differ only as they have a quadratic error. Okay, and this suggests that if you're in the small contrast regime, the renormalization map should just be the average. And averages are really simple to get concentration for. Like if you have a sum of IID random variables, we understand how in 2 lines to get concentration of measure for that. So that's the idea, is that because we can linearize and because the structure of the problem is such that this renormalization map gives you a simple average, you don't need the nonlinear concentration inequalities, you just need the linear ones. All right, so that's our technique. I have a slide I think I'm going to skip because it's like trying to explain in more detail how you fix the DeGiorgi idea by adding a second subadditive quantity, which is dual to the first. because the first was the Dirichlet quantity and the second is the Neumann quantity. And you have to use them somehow in combination to get that idea that DeGiorgi had to work. And the different sort of one inequality is like a lower bound for the matrix, one is an upper bound, and you kind of show that they eventually converge together to the homogenized matrix through some iteration. But maybe I skipped this slide because I want to state the theorem. So what is the theorem that we state? And this theorem, of course, there's many flavors of it. You can change your problem from the checkerboard or finite range dependence to other situations where the coefficient matrix has decaying correlation. I mean, there's a million, there's a zoo now of theorems. But the basic theorem says that like okay, so you have to decode the notation a little bit, but this phi that looks like the domain of the integral just means that I'm integrating with respect to a heat kernel, dx. So I'm sort of averaging the corrector field and averaging the difference between the fluxes and the homogenized flux and seeing that how big they are when I average them over scale r. And I get r to the minus d over 2, r to the minus d over 2. This script OS means that I have almost Gaussian control of the tails. So like the probability of outlier events and stuff. You have something that's the same for the energy. And you can, if you have weak information on the gradient, you can integrate over scales to get the size of the field itself. And we can make that small contrast argument actually spit out that our functions actually converge to the Gaussian free field. That is this quantity over here, which is like the corrector field's gradient averaged over a heat kernel. We can actually show that there's a CLT for that, not just that it has fluctuations the order of the CLT, that if you divide by r to the minus d over 2, it converges to a random variable. And as you move around the mask that you're integrating with respect to, you get correlations, and those correlations are the Gaussian free field. So it looks exactly like you would think. Okay, so I had a whole slide where I was going to make a joke about try to compare the two methods. Okay, and I think I'm running out of time for that, but I hope you enjoy my Star Wars meme anyway. I was going to talk about the pros and cons of the two methods. Okay, so just very quickly, I'm going to not surprise you by trying to convince you that the coarse-graining method has advantages. And some of its advantages are, just really quickly because I'm running out of time, that the first two steps, which were the sort of easy part of the whole program, are kind of super robust and can be applied to many different kinds of problems. Okay, so you can make the equation degenerate; it doesn't care. You can, make your problem, instead of being a nice uniformly elliptic equation, you can make it on a random graph, which is barely connected. That we're just down to the connectivity threshold, and we can handle it. It's fine. It gives sharp stochastic integrability on all of the model cases, including Gaussian correlation decay. And what I like is that it's mostly analytic. The only time you ever use a probabilistic argument is when you say, oh, but this is a sum of independent random variables. And so I know the size of its fluctuations because I know how to use independence. Even I can do that. So you don't need heavy probabilistic tools mixed up. But these can be used in combination in a really nice way. I mean, nonlinear concentration inequality methods are nice because they can spit out the optimal scaling of the error in like one line. Because as soon as you have the regularity done, which would happen in steps 1 and 2 of our program, you can then plug into the concentration inequality and it'll spit out bounds. And this kind of stuff has been done. Okay, I have to hurry up. I wanted to mention that, so I didn't spell degenerate right there. I wanted to mention that just as evidence that we can handle degenerate equations, Paul and I wrote a paper 6 years ago, which does quantitative homogenization on the percolation clusters. So this works all the way down to the critical percolation probability. So you have the local structure of your problem is such that you have a graph that doesn't look Euclidean at all and has crazy local geometry. Okay, and the way that this fits into our program really nicely is we can zoom out, kind of renormalize until the graph looks Euclidean, and then we can start thinking about homogenization. And because our methods don't really see the small scales, it's like you can start at some scale And it's like when you renormalize the graph so that it looks Euclidean, you've kind of made your problem uniformly elliptic, in a sense, in the sense we need to run our proof. Whereas if you wanted to use a nonlinear concentration inequality, if you try to differentiate with respect to the environment now, you can like disconnect the graph, and so that those things do see the small scale in a way that you don't want to see if you want to solve this problem. And so that's one advantage. Okay, part 3. I know, so I think I've already run out of time. If it's a 50-minute talk, I'm like 51 minutes in. But let me just tell you what I think the nice open problems are, because you probably want to ask that anyway. I have 3 problems that I thought I would say. The first problem is, and I think that this is what should be the main problem, frankly, is to try to obtain quantitative homogenization estimates in large contrast. And I really mean, so there are some large contrasts that we can do. Like if you have a degenerate coefficients or large contrast, but then if you zoom out a little bit, it's renormalized to be of order 1, then we can handle it no problem. But what I really want are really your worst nightmare of a situation. And what can you do in the worst case when you can't use an ad hoc one step to fix the degeneracy? And this is probably very hard, because you can kind of encode critical percolation problems into it and see that you probably are going to have a hard time doing this. But I think that this would be a very nice, this is a problem that should be attacked just because it's of fundamental importance. And without it, we'll never make progress on things that really do have a lack of scale separation in the random case. Problem 2 is I wanted to say, make direct connections to renormalization group methods in mathematical physics. There are renormalization group theories in mathematical physics which are applied to things like the gradient models that I was discussing. It'd be really nice to know that the homogenization methods and their renormalization group methods, maybe some, like maybe they're just 2 different languages for the same thing. I don't know. But it'd be nice to sort of see if there's a connection. These gradient models really do apply to, they're toy models for really important math physics problems, like the 3D easing model and interfaces for that. And so if you could make progress, more and more progress on the models that get closer and closer and closer to that, it's plausible that you could use homogenization to kind of encode the renormalization that you need to solve these problems. Okay, the last one, I was just going to say, we don't really understand wave propagation and spectral problems very well in the random case, because those require super high order correctors, like infinite order expansions, and we don't know what to do, even in the periodic case, to be honest. And in the random case, we know nothing. Okay, thank you for your patience. Nobody interrupted me with a question until now, maybe because I was talking too fast, but I'm happy to take your questions now.
Okay, so thank you very much. Do we have any questions? Okay, we have a comment in the chat. I would like to bring attention to the recent preprint of Colombo Crepa-Sorella on anomalous dissipation for passive scalars that also uses shear flow.
Yes, let me see. Yes, that's a good point.
Is...
Yes, so they put a paper on the archive.
It's from me. I apologize. I'm at a conference, so that's why.
Yeah, no. If I would, I would have spent a long time quoting them if I was giving a talk on just that topic. But a few weeks ago, so they put this preprint on the archive that does something very close to what we want. It's a little different than what we're doing because they don't have sort of infinitely many active scales. They have in space. They have like one scale in space happening at a time. And so their thing like kind of builds anomalous dissipation at the last final time. And what's interesting about their thing the most, I think, is that they also get the regularity for the scalar, which Vlad and I also have the regularity for the scalar as well, but they get the regularity for like a larger range of parameters, which we don't know how to do. So their preprint is super. I thought it was a super interesting thing when I saw it. I was kind of sad for half an hour because I thought I was scooped. And then after that, I was happy because it's actually great. And there's things good about both papers. Their paper gets more parameters, and they can go all the way up to the Lipschitz for the vector field. Ours gets stuck on the kind of 1/3 on Sauger exponent, but our vector field is maybe more like a fluid. Yeah.
Thank you.
Thank you. Do we have any other questions?
Also, their paper is written, which is also good.
Okay. So I just had one quick question. Do you have other examples in problems from statistical physics or mathematical physics where you would need to homogenize something over many scales, like not only 2 scales, like it happens in homogenization, like in the standard problem that you...
Where you have like a cascade of scales?
Where you have, yes.
You mean like the anomalous dissipation guy?
Yes, for instance. And does it, do you know if it appears in other like...
Yes, I mean, like if you were, okay, so people, so when you talk to probabilists, they ask you, can you homogenize in the case when the matrix is the exponential of a GFF in 2D? So it's like the, okay. So if you have Gaussian multiplicative chaos as your coefficient, what that means is that the homogenized matrix looks like a whole bunch of scales, like it's like IID random fields of different scales, and you have one for every scale. And instead of adding them, you multiply them. And so that's really bad, because that means that you have kind of high contrast, but your renormalization group has to like accomplish a certain amount of decreasing of the contrast before the next scale comes and increases it again by multiplication. You know, it's not addition. And so that's a disaster. And I don't know, I can do subcritical versions of that. They're in my Dropbox file that will probably never be submitted, but I can't do that. And that is going to be like another cascade of stuff like that.
Okay, sounds good.
I think Michael Weinstein has his hand up.
There's a question.
Thanks for the beautiful talk. Years on the topic of connections between PDEs and renormalization group, years ago there was an application of renormalization group by Brickmont and Kupiainen to study the formation of singularities and other asymptotic problems in parabolic evolutions. And I was wondering, is there any kind of tie-in to any of the ideas that you're talking about?
It depends on which Brickmont and Kupiainen paper. They have one paper that I know pretty well, and they have another bunch of papers that I don't know very well at all, because I actually, yeah. So there's one paper that we call the drift problem, which is that you take a Laplacian and a little tiny drift, but the drift is it's not solenoidal, it's not divergence free, and it's not a potential. But it has a symmetry condition so that it can't go in one direction. And you try to show that as you zoom out, so as you zoom out to larger scales, the drift should dominate. But you try to show that homogenization happens fast enough that the drift homogenizes itself away faster than it can hurt you as you zoom out. And this should be a good application of our renormalization group methods, I think. I mean, so Felix and I were working on that together 8 years ago, but then we stopped working together, and that problem was on our to-do list and it kind of died. I don't know, Felix, are you planning? I don't know if he wants to answer, but I don't know if he's thought about it. But yeah, that problem is in our radar and is in our target list, but we haven't done anything about it.
I think Ben Furman is the one who knows it also quite well, right? Especially the work of Snitman and Zaitouni, which do use some kind of renormalization argument.
Yeah, so I think Brickmont, Kupiainen, sorry, go ahead, Ben.
No, go ahead.
So I think Brickmont and Kupiainen have a renormalization group argument that Ofer says he says there are certain parts he couldn't follow, so he and Snitman wrote the whole thing again. Using sort of similar ideas, but when you go to write a 110-page paper, any two people will do it a bit differently, and so I think that it came out a bit different. And I think because Snitman was on that paper, there's not a single typo in the paper, so it's correct, but it's also 110 pages of very difficult reading. So I tried to read that as a postdoc, and then I tried to work on it with Felix, and we have sketches that are convincing, but we've not implemented the proof.